Hey class, welcome back to Electromagnetics. So this lecture we want to take a quick look at reflection and refraction of plane waves. Thought for the day though, for now we see only a reflection as in a mirror. Then we shall see face to face. Now I know in part, then I shall know fully, even as I am fully known. So I think one of the points of this scripture is that when we read the Word and when we commune with God, we do see a reflection in a mirror of what our self is, but until we see Him face to face, that won't be a full reflection. It would only be in part, and then we're not fully known and we don't fully know Him. But we need to continue to strive toward that. I thought this was pretty applicable today as we look at reflection and refraction, because just as this example in Scripture, we'll see that electromagnetic waves, only parts reflected, not all of it, and so we can only get partial part of the wave. So kind of an interesting correlation there. So up to this point, we've considered several different scenarios where electromagnetic waves propagated in particular direction and conditions and the attributes of the propagation. So we've even looked at situations when electromagnetic waves have encountered a boundary. We developed, used Maxwell's equations there to develop the boundary conditions, but these were very special conditions when the propagation, the direction of propagation was normal to the boundary. So now we want to go back to that and think about what's going to happen when the electromagnetic wave again encounters a boundary that is a change in intrinsic impedance, but not at a normal angle, but at an oblique angle. And we have some very interesting things that happen here. So let's set this up. So here's our boundary. This solid line is our boundary. So we have medium 1 on top. And of course, it has some permittivity and permeability. And then we have this boundary, and then we go into medium 2, which has some different permittivity and maybe permeability. And so instead of hitting it straight on like we used to do with this dashed line, when we developed our Maxwell's equations for boundary conditions, now we're kind of coming in at an oblique angle. And so we're going to measure this angle from the normal. So this theta I is what the angle is. How much off are we from hitting it normal? So what we're going to find out is that at this boundary, we'll have two things, or the opportunity for two things to happen. One is that we'll have some of the wave will be transmitted and some of the wave will be reflective. And what we're going to find out is that these angles are not always equal. And so we're going to examine that a little bit. So in order to satisfy the boundary conditions, I mean, we still have to satisfy Maxwell's equations, but it's a little different scenario here. Again, we'll have this reflective wave that's going to be set up, and we'll have this transmitted wave set up. So these are the definitions that we're going to be looking at here. So the difference in the angles of the two resulting waves is a result of the effects of the material properties on the phase velocities. So the relationship between these velocities and the angles of the waves that we just looked at in the previous graph are governed by these equations. So we've got a phase velocity in material 1 divided by that theta sub I. Phase velocity again times the theta sub r, the reflected, and then we'll have this new phase velocity in the second medium, and that's going to have a relationship governed by this, that governs this theta, this angle in the transmitted material. So we need to remember in general that this phase velocity again is a function of the material itself. So this is what's going to govern this change, is the change in the permittivity and the permeability. So now if we look at this, it should be pretty evident that the theta I and the theta r, that is the incident and reflective angles, should be equal because the phase, we're in the same material, so this phase velocity will be the same. The change is going to come that we'll notice the most is in the second material, because we'll have a new phase velocity which will give us this new theta t. And so one way to think about that is And the reason why the angle would be different, maybe you've seen those zero-turn lawnmowers like the Skags, or if you've ever driven one, you have a handle in each hand, and so as you're moving along, you'll go straight if you keep them at the same position. But if you start to pull back on just the right one, that's when you start to turn, and that's kind of what's happening here. It's the same phenomenon. When we hit this material, it's causing a little bit of a drag on the electromagnetic wave, so it causes it to bend a little bit. And it's not exactly what's happening, but it's kind of a good analogy of what's going on there. So if we now substitute the definition of phase velocity into these equations, what we're going to see then is we can solve for this the sine of this transmitted angle. So it's the ratio of the phase velocities times the sine of this incident wave angle. And so again, if we put the definitions of those in, we see again it's going to be a ratio of the characteristics of the material. So if we solve for the angle itself, this transmitted angle is going to be the inverse sine of this ratio times the sine of the original angle. This is known as Snails Law, and so this is what governs this. So this is actually, maybe you've seen the demonstration of using the prism like Isaac Newton did, and it bends the colors, bends the white light into the different colors. They actually come out at different angles. Snell's law plays a role in that. It's also known as the law of reflection. You might hear it called that. Or you might hear it called the law of refraction. These all refer to the same thing, and that's this relationship here. So we now want to introduce a new term, or definition, and you've probably heard of this term before. It's called the refractive index, which is defined as this. So this N1, it's the speed of light in free space divided by our phase velocity in our material. And so when we enter the values in, we get C times mu1 eta 1, which is just the square root of the relative permittivity and the relative permeability. And so if you've ever done anything with photography and dealing with lenses and photography, this is what makes a lens work. So it's making sure glasses work. It's this refractive index. It has a property that causes the light to bend, and you can focus it on like the back of your eye, or on the shutter, or the digital element in the camera. So using this definition, we can now rewrite Snell's law as follows. And so now we see that this new transmitted angle is the inverse sine of the ratios of the indexes of refraction times the sine theta I. So again, just like when you do your glasses, air has an index of refraction, and then the glass material that you use for the lenses has a refractive index. And so that ratio is what's causing that light to bend. So if the two dielectrics are non-magnetic, which is probably the case most of the time, we can even simplify this more to say that the relative permeability is 1. So now we're just looking at the ratio of the square roots of the permittivity that govern this angle. So we now want to determine the reflection and transmission coefficients. Remember, that's what we did before with Maxwell equations of the normal, when we're hitting the boundary from a normal angle. But how does this affect these coefficients now that we're doing an oblique angle? So again, we look at this now in terms of electromagnetics. If we have a wave coming in here, incident, and so we're going to have our E fields oscillating in and out of the screen, and then our H field, our magnetic field, is oscillating back and forth this way. So they're transverse to the direction of propagation, so it's coming in then this way at this angle theta 1. So after it hits, some of the electric field still coming in and out of the board will be reflected and going up at this angle. The H field, or magnetic field, is now transposed, now moving this direction, and our transmitted wave into the new medium. Again, the E field, electric field, is going in and out of the board, and H field is modified by this angle itself. So what does this look like? So now by correctly applying Maxwell's equation to boundary conditions, and this is much like what we did before when it was the case when they were hitting the boundary at a normal angle, but now we're doing it at an oblique angle. Again, I'm not going to go through that whole derivation here. We see that we can define this new reflecting coefficient, and this is for the perpendicular wave. So in this case, based on the graph or the image we showed you in the last slide, this is the ratio of the electric fields because they're going in and out of the board. It's going to be this new equation, which is dependent on the intrinsic impedances of both materials, which we're used to from the perpendicular case, but now we have to put these cosines of these angles into that equation. Likewise, the transmission for the perpendicular case, again, in this definition is the electric fields, ratio of the transmitted wave over the incident wave. Again, it involves the intrinsic impedances and the cosines of the angles coming in. So this is the new definition for the oblique angles. And so, we take note here that, if we are coming in perpendicular, the cosine of these angles then would be 1, and we have our original equation, right? So this doesn't look too unfamiliar to us. It should. Hopefully we've just modified it now for oblique angles. So these are known as the Fresnel reflection and transmission coefficients for perpendicular polarization. So again, we have to keep in our minds that there's two different polarizations going on here based on that image we saw before. So we now want to determine the reflection coefficients in the case for the magnetic field, where the magnetic field is perpendicular to the plane. So here we can do the exact same thing. Now we've kind of flipped things, right? Before we had the E field going in and out of the screen. Now we have the magnetic field going in and out of the screen, and the E field oscillating back and forth parallel to our screen. So again, we use Maxwell's equations, and we can arrive expressions in now for these parallel coefficients. So now we look at this time the E field is not going in and out of the screen, like we said, is parallel to the plane. So this is our parallel reflection coefficient. And here, again, this looks similar to what we saw before. And again, the parallel transmission coefficient definition. So again, these are known as the Fresnel reflection and transmission coefficients for parallel polarization. Now that we have these definitions, I want us to take a look at some special cases to help us understand, some different things that are going on here. So for the first one, we want to take into look at the condition where theta 1 is equal to 0. So this takes us all the way back to where we originally defined our boundary condition, right? Where normal, the incident wave is normal to the interface. So again, like I pointed out before, the parallel and the perpendicular reflection coefficients are equal in this case, and we have the equation that we are used to, just the ratios of the intrinsic impedances. And again, the transmission coefficients, both perpendicular and parallel, again here are equal as well. So now we want to look at another special case. In this case, we're going to look at when the perpendicular reflection coefficient is equal to 1. When that happens, if we go back and look at those original equations, because they differ by the theta angles where they're present, they're reversed for the parallel and perpendicular case if you go back and look. So in this case, the parallel reflection coefficient would be -1. So this occurs when the cosine of the second angle, or the reflected angle, is equal to 0. So if we assume a non-magnetic material, again, which is almost always the case, this would imply then that this theta c is the inverse sine of the ratio of the square root to the permittivity. Well, this is known as the critical angle then at this point. And so this is very important because at this point we experience a phenomena which is known as total internal reflection. So what this means is that the time average power of the incident wave travels along or is reflected along the boundary, never crossing it. This is super important, and we're going to look at a pretty substantial application of this that we're all familiar with and utilize every day, but we'll talk a little bit more about that in the upcoming lecture. So to explain this mathematically, you'll hear the term evanescent field or wave, and so this is how we account for the imaginary wave that has to be present. The math tells us, at least. So it's not really anything that we've successfully measured directly, but we can definitely see it. I've actually worked with this in this field in some of our experimentation. You know, it has to be present, at least, to make the math work out to what's happening physically. So again, when we look at this theta c, or this critical angle, you know, that means the wave's coming in here, and then when it hits, we're having all the wave either travel along this boundary or all of that part of the wave reflected back into medium 1. So now we want to look at another special case, and that's when the reflection coefficient, at least the perpendicular one, is equal to 0. And so the only way this would happen is if this equation is true, that is, intrinsic impedance. The second is times the cosine of the incident wave is equal to the intrinsic coefficient, intrinsic impedance, in material 1 times the cosine of theta 2. So for this case, if you work out the math, then the square of the sine of theta 1 would have to equal to this expression involving the permittivity and permeabilities in the first and second medium. Well, for the usual case of equal permittivities, that is non-magnetic, this equation has no real solution for theta 1, and hence there is no angle of incidence for which the reflection coefficient is 0 for the perpendicular polarization case. So just another special case that we want to look at here. So another special case we want to consider is if the reflection coefficient of the parallel component of our wave is equal to 0. And so in this case, now we have this condition, where before we had theta 1 here and theta 2, so now that's reversed. So for this case, we have this relationship involving the physical characteristics of our mediums. And so if we again assume equal permeabilities, that is non-magnetic material, then we now have this special condition that we can solve for, this theta p, which is this theta 1, is equal to the tangent squared of the square root of the permittivities. So this means that the reflection coefficient is 0 for the parallel polarization. So again, this is utilized in the real world. So we now want to consider a special case when this parallel reflection coefficient is equal to 0. If we apply these conditions and solve, that we had before, we utilize this equation again. So at this point, we have a very special condition in that the parallel components of the electromagnetic wave are totally transmitted. So this means, we had the component that's going in and out of the board, and then we have which is the perpendicular case, and then we have, it's oscillating back and forth inside the plane. So what we're saying is that component, whether it's the electric or magnetic, it doesn't matter, it's going to be fully transmitted into the new material. So this basically means that the EM components of the incident wave are separated by 90 degrees. So with one component in one medium and the other component in the second medium. So this is a form of polarization, and this special angle then is referred to as Brewster's angle. So maybe you're familiar with the concept of polarized sunglasses. It's not a super good example, but it is related. So that's what's happening when you have polarized sunglasses. It's only allowing one component to go through uh, the lenses into your eye, and so that's what changes the effect of things there. The crazy thing is sunlight is not polarized. You have components in all directions, but as soon as it bounces off of any reflective material, like even the ground or the walls or anything, that will polarize it. So funny things can happen when you start to polarize electromagnetic waves, and even separate out perpendicular and parallel components. There's a whole field of study on that. It's actually pretty interesting. So one application of that is what's known as the Fabry-Perot resonator. And so the way this works is they have this cavity, kind of like we had with the waveguide, where we put, we had a rectangular waveguide, but then we put plates on the ends of it and created a cavity resonator. So this is the Fabry-Perot resonator. And so what this is they actually put a little slant in here with this second material, this glass window. So you have some gas in here that has some permittivity and permeability, and then you have this glass here that has a different permittivity. And what it does is it causes it meets the conditions of Brewster's angle, so that now we only get one polarization of the angle here. And so what happens is, they start the process, they usually shine some light in here, and then it goes through this little slit, and then goes to this next one, so it polarizes, hits the mirror, goes back, hits this mirror, and keeps going back and forth, and they keep introducing more energy or more light into it. And so you get this resonating effect, and so that actually amplifies it. And so this was one of the first applications where they were able to produce some form of a laser. So that's what a laser is it's light that has amplified and has the same polarization in one direction. So we create lasers differently now. We do it with electronics, semiconductors, but this was one of the first ways they did the Ruby laser, which of course Einstein predicted with some of the work he did in the theory of relativity. So it's pretty amazing stuff. It's actually pretty interesting.